This is similar to the previous problem, except that in this case, both A and B will move in opposite directions and eventually end up meeting. A travels to the right with a uniform velocity of 40 meters per second, and B travels to the left with a uniform velocity of 10 meters per second, and they end up meeting at point C. The initial distance between A and B is 400 meters. How long would it take for the red and blue balls to meet at point C? Just like we did in the previous lesson, let's first solve this using the equations of motion, and then let's solve it again using the concept of relative displacements and velocities. We first focus on the red ball A. It travels from A to C with a uniform velocity of 40 meters per second without any acceleration. We use the second equation of motion but without the acceleration component. So we have x minus x0 equals v0 times t. We fix the origin at point A. The initial displacement at A is 0. The final displacement is the distance between A and C, xac, which is not known to us. The initial velocity is 40 meters per second, which is the velocity right through. Using this, let's obtain our equation 1. Now we move on to the blue ball B. So now we shift our focus to B. It travels from B to C with a uniform velocity of minus 10 meters per second. Minus since it travels in the negative x direction. Again we use the second equation of motion with no acceleration. Our origin is at point A. So the initial displacement xab for ball B is 400 meters. The final displacement is the distance between A and C, xac, which is unknown to us. The initial velocity is minus 10 meters per second, which is the velocity all the way for ball B. Using this, we obtain our second equation. We subtract the second equation from the first, so the displacement term xac cancels out, and we get the time t as 8 seconds. We have solved this problem using the equations of motion. Now let's solve the same problem, but this time let's use the concept of relative displacement and velocity. So as a first step, we need to attach the frame of reference to one of the objects, and let's select A. Now A moves from the ground frame of reference at 40 meters per second, but from A's own frame of reference, we will consider A to be at rest, and we will have to obtain the displacements and velocities of B with respect to A. Here the velocity of B with respect to A will be Vb minus Va, which is minus 50 meters per second. So A will see B approaching it along the negative direction of the x-axis. This is the animation as seen by an observer in the ground frame of reference. Now let's see the animation from A's perspective. This is how A sees B approaching it. It considers itself to be at rest and sees B approaching it at 50 meters per second, whereas from the ground we see B traveling to the left at 10 meters per second. The initial displacement of B would be xb with respect to A, which is xab and is given as 400 meters. And the final displacement would be 0 as B will meet A here, with A being at rest. And B is approaching A with a velocity vb with respect to A, which we had computed as minus 50 meters per second to the left. Now let's plug all this into Newton's second equation of motion. And in this equation, we are plugging in all the data as seen by A, so everything is with respect to A. So we have x minus x0 equals v0 times t, and all the values to be plugged in should be from A's frame of reference. So substituting the values, we obtain 0 minus 400 as minus 50t. Solving, we get the time t as 8 seconds. Again, you can see that once you have fixed A and then obtained the initial and final displacements of B with respect to A and also the velocity of B with respect to A, plugging this into the equations of motion gives us the answer.